just askew. So we've got this assignment out, sketch 2 direction fields. I want to warm up with one today. I want us to do one together because I want to do it on the board because I want you to see what I want to see. And it may or may not be what you have. I've been seeing some folks thinking, that's not quite what I'm looking for. So let's just practice one really quickly. Let's do a relationship one. And there's a new web work up. That was disappointing. Next. That's better. There's a new web work up. I think it's called Planar Systems 1. You can definitely do the first 2 problems in there as of the last class. So that the first 2 problems here will be the stuff where your solutions are going to look eigenvalue corresponding eigenvector plus second eigenvalue. This is 2 distinct eigenvalues. So this is x of t, y of t. This was just basically a quick summary of what we did last time. This is for the system where you've got x, y dot equals some matrix A times x, y, and we have eigenvalues, lambda 1 and lambda 2, corresponding with the vectors v1, these dudes here. I'll just make it right. So that's what those first 2 problems are all about, that thing. Today, what I'm hoping to do is talk about, and here, this is lambda 1 is not equal to lambda 2. What I want to talk about today is the case where these are not real. So I should also put that in here. Lambda 1 and lambda 2 are real values. Today we're going to talk about what happens when you have complex eigenvalues. With this, let me just do a quick summary before we do our problem together. And this might even help you in the sketching we're about to do. If lambda 1 and lambda 2 are both negative, your phase portrait's going to look something like this. You're going to have some eigendirection. Oh my God, where's the redo? Bro, all right, let me start in the center. You're going to have some eigenvector v1 that describes an eigendirection like that. So you've got this whole line, and then maybe you've got a v2 that looks like this. So this is the lambda 2, this is the lambda 1. And in fact, since these 2 are not going to be the same, they're 2 different negative numbers. One's going to be faster and one's going to be slower. And off the top, I'm going to have to provide you with a little more guidance on this. But these will both be inward flows on these directions. So thinking of this as the e to the whatever. So if I've got e to the lambda 1t and that lambda 1 is negative, this is a diminishing quantity as time flows on. And you can think of these negative eigenvalues as corresponding to a sink kind of action. So you've got a sink here, a stable equilibrium at 0. So you expect your flows to be inward, and you'll have something like this for your trajectories. I'll give you a little more guidance on that. I'll write some up. If they're both positive, then do the same thing. Get your eigendirections. I guess I'm going to make these look a little different and try to make them look good. Okay, So these are going to correspond to outward flow because you're going to have e to the lambda 1t, but that's a positive number there. So as t gets bigger, that value gets bigger. Look at those solutions. When those exponents, if lambda 1 and lambda 2 are positive, e to the whatever gets bigger. So you're moving away as the t gets larger. So what you'll see here on these directions, let's say this is v1 and this is v2, you'll see something like this, outward flow. Still do all the things we're going to do in just a minute, but you'll have nice trajectories that look like this. And so this is a stable equilibrium at 0, at the origin, the 0 vector. This is an unstable at 0. And then if the two eigenvalues are an opposite sign, and I'm going to say that in a really interesting way. Lambda 1 times lambda 2 is negative. So think about, when would that happen? It's when they're opposite signs. The only way the product could be negative is if one's positive and one's negative. So along this, you're going to have v1, and let's say here this corresponds to lambda 1 and lambda 1 is negative, just for the sake of it. That means I have inflow on that. And for the other one, I've got v2 and lambda 2. God, lambda 2 is positive here. That's an outflow. And so this is the other possibility. It's really going to be one of these three systems. This is called a saddle node at equilibrium. Here's your equilibrium in the center here. But a saddle node is where you kind of got this hybrid of attraction and repulsion. And you get these interesting kind of literally hyperbolas for your trajectories. So with that in mind, let's do one. So practice. And maybe I'll just work this one through so that you can see what I'm looking for. Let's say I've got Zoe spelled with an X, and that Zoe is relating to what's a good Y name? What's a good weird Y name? Yolanda. What's that? Yoda. Oh, they're both pretty good.
What about Yanny? Like Yanny or Laurel?
Yeah, I don't even know who that is. That someone?
No.
Okay, sure. So, okay, is Zoe and Y is Yanni. Yeah, there we go. Or Yolanda. I like them all. Or you're an X-wing fighter and you're interacting with Yoda or something like that. Whatever. I like them all. So we've got Zoe's. We're definitely sticking with Zoe on the X. Relationship. This is Zoe's velocity of love. Remember how that works. X equals Zoe's feelings toward Y. And I'm probably just going to say X and Y from here on out. So this is negative X plus Y, and then Y dot, the velocity of Y's love for X, is going to be just purely based on Y's feelings. So let's say put a minus 2Y there. Y is super self-involved. It's really like nothing gets in. Not even watching the expressions on X's face. Just like, I feel pretty good about Y. And that makes me, what happens when Y actually feels positive about X? What happens to their love? Can we look at this and decide? It goes away, it dissipates. When Y is positive, when Y is in love, y dot is negative, so the love dissipates. What about when y is in, what was it you said, contempt? When y is in contempt for x, what happens? When y is negative, what happens to their feelings? It increases and heads toward zeroness. So we've got y kind of always, if they're in love, they're falling out of love. If they're in contempt, they're falling into love, or at least less contempt. So we've got that, but then x has got this kind of more complicated relationship with y internally. So let's sketch the phase portrait. And here's what I want you to do for your phase portraits. And you stole this. Step one, show me all this stuff. I want to see all this stuff. Now there's no eigenvalues yet for that assignment. That's on the web work. So sketch a phase portrait. A phase love portrait. Step one, find the null lines. I want to see it. Please show me all this stuff very clearly in your assignment. I want to be able to find it. I don't have to go looking for it in some weird field of scratches. Find the null lines. So x dot equals 0 when, make it very clear, when negative x plus y equals 0, i.e. when y equals x. Let's keep our system up there so we can refer to it, but let's do our portrait right in the middle. Did I start recording? Okay, cool, thanks. Clearly some short-term memory issues here. X and y. Somehow I remember the math. Math always sticks. So the x dot null line is all along this line here. So and I would label these because it kind of helps. It helps to keep your head together, just having that on the page. And it also helps keep me super happy when I can just look at your thing and know what is going on. Let's do the y null line. Y dot equals 0. This happens when negative 2y equals 0, i.e. when y equals 0. And that's called the x-axis. So all along here is where y dot is 0. Cool. Now let's figure out the sign SIGN on either side of each null line. So let's look at that x dot null line. When I'm up here, when I'm on this side of this diagonal null line, I can just pick any point. So I'm going to use 0, 1. So I'll make a little table here. So here's going to be x dot, oh hell, why not, y dot, and then here's my point, x, y. And I saw Evan had a chart like this earlier, and I think that's a good idea. He and I were talking. So we had 0, 1, helps keep the head straight. Here I've got 0 plus 1 is x dot, so it's positive. I'll just put a plus there for positive. Erstwhile, y is 1, so y dot is negative 2, negative. Cool. So that means that on this entire side of x dot is positive. X dot will not change sign. It can't change sign until I cross that null line. So out here, I've got x dot is positive, and also down in this little quarter down here. See, it's not as, you don't have to necessarily test every region. And then it's going to be negative on the other side. So positive, whoa, yeah, x dot's going to be negative on the other side. So in that little quadrant, wedge, and then down here. We could test points to prove that to ourselves. The key thing is I just want to know what is the sign of these rates of change in each of these little regions. 1, 2, 3, 4 little slices. Now let's go to the y dot. So y dot equals 0 is this line right here. When I'm above, I already know that when I'm above this line, y dot is negative. So y dot is negative here. And y dot is negative here. I already did that testing. It won't and can't change sign until I cross the null line where it's 0. Cool, so it must be positive down here. There'll be a day when that's not true, but it won't be for a long time. Outstanding. Looks like I've got every flavor of vector in here. Groovy. So next, step 2. This was step 2. So step 2 is determine the sign of x dot and y dot in each. You will have 4 regions. Couldn't hurt to note those on the graph in some way that won't get in your way of actually sketching things. Cool, let's go to x dot equals 0. X dot equals 0. Let's review this. Every vector in the plane will consist of 2 components, a horizontal and a vertical component. This is horizontal velocity, this is vertical velocity. So if x dot is equal to 0, there is no horizontal component, and it's a purely vertical motion, which is either up or down. So all along this line, I've got vertical arrows. Notice that y dot is negative up here, so those are downward. In fact, if I got really precise, they would shrink in size as I got closer to 0. And then down here, as I cross this line, this is where y dot is 0, right here, this axis. So down here is where it becomes positive. Let me stop. Is this working for you? Just feeling good. Any questions on any of this? Groovy. So let's look at this null line. When y dot equals 0, that means I have no vertical component and it's just pure horizontal change. Just pure horizontal stuff. So you're only moving left or right. So I come here and I look at this and I realize x dot is negative in this little area. So that's an inward flow. And over here, x dot is positive in this whole side over here. So that's a rightward flow. Cool, and we're almost done. That's the hard part. That's where the work happens. And then keep in mind that the changes are continuous. So what I mean by that is continuity is a mathematical idea that shows up all over the place, but here we can exploit it. Let's move, what's in this region? I don't even need to know that anymore, because I know that here I'm upward, and I have to somehow continuously change to rightward. So what I would recommend, and I didn't even think of saying this way until Evan and I were talking, but look right in the middle. Like right in the middle here, what is the average of those 2 directions? And it's an upward right diagonal. And then it's like, so right by this one, it's gonna be close. When you're close to a null line, it's gonna be really close. And I had a friend come by who said they weren't very good at drawing arrows or making fine discernments. So I thought this might also help that friend. Take that average, friend, and then you can just average those 2. So like up here, what's the average between pure diagonal and pure horizontal? Something lazier than pure diagonal, like that. Looking good? Look at that, you can picture what's gonna happen here. And then let's just fill in the rest. So from here, hey, do me a favor, try your luck at this wedge. That's a big piece of pie. That's a sweet ass piece of pie right there. What do the arrows look like in it? for that average, right in the middle of that wedge. It might not be exactly that, but that's it. I mean, we're just winging this anyway. If we're sending a rocket into space based on this, God help us. I mean, I hope we're not drawing things to send a rocket into space. I hope we have a computer to help us. It is hard. I mean, it's hard, anonymous friend. It's rough. Especially in these big regions, it's like too much freedom. There's too much freedom here. Yeah, you know, do what you can do. Enough to get a decent sense of the flow. And if yours looks anything like that, bravo, you have done it. It's good news because we're launching in 10 seconds. So it's a good thing we got these arrows right. Can you finish the rest, please? And then we'll check together. The tiny wedges are the best. Almost in these small wedges, it just feels like having that average one really tells you almost enough about what you need. And there will be straight line trajectories. So it looks like I'm making straight line trajectories. There will be, because there will be two eigendirections for a 2x2 system like this, most of the time. So these things that look like straight lines are probably the eigendirections. FEQ life problems. Subpar. Truly subpar, I would say. Oh, that's not flat enough. That's the problem. Okay, so that should be a little flatter. As I get closer to that, it should look more like that. And then it should look, whoa, bruh, wrong way. Flatter like that. It's got to be consistent. Yeah, yeah. What happens to this relationship, no matter where they are? Spiral to zero. Spiral to zero, looks like a spiral. This one won't have a lot of spiral, but there definitely is a feeling of that spiralness. You're right there, Cormac. So when we add our trajectories, we want to make sure that we enforce, at a minimum, just make sure that these null clines are respected. So in other words, when I pass through this null cline, I have a horizontal tangent. And when I approach this one down here, usually the ones that are on the axis, you don't cross, you kind of approach, just so there's definitely that spiraling motion, except this guy kind of actually becomes a little more parallel like that out there. And then down here, as I cross that axis, I want that beautiful vertical tangent, and I want these to be horizontal tangents as I get in there. The key thing to remember is you'll always be headed towards zero in some way. Zero plays a pivotal role here. So you might be headed toward it and then shoot away, and you also might leave it as well. So if these arrows had all been reversed, this flow would have not been this, but it would have, I just changed the direction on those. But we're gonna have some stuff like this coming in here. And that's what those flows are gonna look like, and that's good enough. And then you get out the app and you check yourself. All I want is a good effort that I can read. I've seen some, this is a bad one. I've seen some that look like this. There's a problem. You don't want yours to look like that, because I don't know what the hell's happening there. And my wager is, neither do you, if you did that. So, does this sound good, like what I want for those? If you need to fix, take the time you need. Just get it, that's all. Any questions on this, my friends? Okay, cool. Let's talk about complex eigenvalues. So this relationship, no matter what, fizzles out. This one's kind of interesting. I actually want to talk about that red one. One day I'll have you tell me a story about what's going on with some folks. So what if they had started here? That was the initial condition. This is always just so fun to me to think. This was like one of the greatest moments in my life when I realized we could do this, like model relationships with these things. You start out here. So right now, X is not too fond of Y. Y really likes X, right? Got a positive Y value, got a slightly negative X value. So right here, X is in slight contempt. Y is in completely enthralled. And as time moves on, X's opinion improves of Y. X is starting to feel it. Starting to feel it. And the more X feels it, the less Y feels it. So Y's losing it. And then there's like this moment right here when, I don't know, maybe it's spring, everything's just really nice, they're both in love, it's great, it's a lovely day. And they stay together and just kind of like dissipate into, well, I guess we're together forever, so let's get married, or something like that. So I don't dislike you. I'm not back on that beautiful spring day under the tree, but it's okay. So, good stuff. Clearly I'm amusing myself. So, complex eigenvalues. I already showed you at the beginning of the hour what it looks like when we have two distinct real eigenvalues. There's three situations: attractor at the center, repeller at the center, so sink, source, or saddle where it's a combo effect. This is very different. So let's look at the case where A has two complex, it's an M, eigenvalues. And let's call them alpha plus I beta and alpha minus I beta. So now some of you have had complex analysis, some of you are in modern geometry, and like all we do is talk about I in there. Does anyone need a quick refresher of what this means? Are you cool with complex numbers? Just like give me a sign. Cool, thumbs up, cool, got that. Yeah, I got some thumbs. I'm also seeing like horizontal thumbs, and yeah, just a quick review, quick refresher, because it's kind of important before I actually spend 15 minutes doing a derivation with them. Let me clear this up so we have a clear view. Okay, quick review. I squared is -1. It's this number that is called imaginary, and it's the worst name ever given to anything in mathematics because it's anything but imaginary. It actually is at the heart of so many things. Anytime you see oscillations in a system, any physical system, chemical, physics, anytime there's oscillations, I is lurking in there. I is all about oscillations. And so the fact, you might expect some oscillation to be occurring today. We might see some orbits and some real nice spirals this time. Core makes some actual like really lovely spirals, things that spiral in. So I is a number for which this is true. There's no real number that is true for. Sometimes you see this as the definition of I, the square root of -1. We can think of a thing called a complex number as a mix of imaginary things and real things. This is called the complex plane. So the complex plane has a real axis and an imaginary axis. And the really cool thing is you can think of complex numbers almost as points in the plane or vectors almost interchangeably. So if I have some complex number, I wrote this thing up at the top, alpha plus I, B. You can think of that as the point in the plane alpha comma B, x, y. So in some ways this I separates the beta from the alpha, and they can't really mix in any way. So the number alpha plus I beta means I move over alpha on the real axis and beta units on the imaginary axis. So that's alpha plus I beta. Let me give you a solid example. That's all very general. What if I had 2 plus 3i? So that's 2 on the real axis, 3 on the imaginary axis. 1, 2, 3. So there's that number. The number 0 is just this. It has no real and no imaginary parts. It's just 0 of those and 0 of those. Over here, let's see, let's just pick one out. Let's say I had this number right here. That would be -2 plus 1i. I wouldn't write the 1, but I could, and that would be okay. We've all seen this now. It's just kind of like you've seen this. Even horizontal thumb folk. Yeah, okay, cool. All right, good stuff. Definitely scan, I'm trying to scan, keep things anonymous. Cool, so let's actually talk about why is oscillation at all a part of this? Why does I intimately relate with oscillation? Because we can look at powers of I. So let's make a little table here. I'm gonna say I to the nth power, and here's n. And we'll start with 0. And this really is going to be a very trivial kind of thing, but it actually tells us, oh my God, there's something weird going on here. So any number to the 0th power is 1. I to the 1st power is just I. I squared is by definition -1. I cubed is equal to I squared times I, so it's negative I. I to the 4th is I squared times I squared, so it's -1 times -1, it's +1. And now I'm back to there. And I to the 5th is I to the 4th times I to the 4th is 1, so we're back to I. And then we go to -1. And I to the 7th is -I, and I to the 8th is 1 again. And this keeps on rolling. So in the complex plane, what does that look like in the complex plane? So if I'm here, the symbol, this is the symbol for the real numbers, this beautiful R. The symbol for the complex numbers is a beautiful C, like that kind of Gothic style. Cool, got a bar, like super powerful. This is the imaginary part right here, imaginary axis. So let's look at these powers of I. Here's 1. Here's I. I'm just going through this list. Here's -1. Here's -I. And I just keep cycling among those. Just keep spinning as I keep taking higher and higher powers. There's already circulation happening, right? This rotation around the origin. So it won't surprise us as badly when these turn out to represent circulation in the plane. Does this sound good? We don't need to know much more, honestly. This is about it. There is one thing, I'm just gonna knock this out and get this astounding fact out of the way. I shouldn't be brushing it off like this. Let's talk about Euler's identity. I'm going to write this up. I'm going to justify it briefly. Has everyone had Calc 2? God, I hope so. I think it's a prereq, right? So, I really hope so. So Euler's identity says that e to the ix, and x can be anything. So that's weird right off the bat. I've got e to an imaginary power is cosine of x plus I sine of x. In fact, e to the ix is just a number on the unit circle in the complex plane. And if you know your trig well, it's just the number that has angle x right there. So this is e to the ix right there. Your cos is your horizontal component, your sine is your vertical component. So you can just think of e to the ix as a number on the unit circle there. Now why? Well, let me give you a quick proof. Really quick, super quick proof. Because I feel like I can't just say that. And I feel like if this is your last math class, you can't not know why that's true. So here's my favorite proof. Think back to Taylor series. And this is the Calc 2 thing. We know that e to the x has this Taylor series. If you want to remember one Taylor series for the rest of your life, you can get a lot. You can get a lot knocked out with that guy right there. I also know that the sine of x is x minus x cubed over 3 factorial plus x to the 5th over 5 factorial, and now it's just these odd powers. Kind of every other term here with the sign alternating. And then, let's say I didn't remember what that was. Calculus. What's the derivative of sine? It's cosine. So I can just differentiate this series here. See, we're getting a lot of stuff in here. If your Calc 2 teacher didn't show you this, you should file a complaint with the provost. Don't reference me. You're on your own after that. So take the derivative of that, you get cosine. What's the derivative of x? It's 1. What's the derivative of x cubed? 3x squared. The 3 comes in front, cancels with the 3 in the factorial, and leaves me with x squared over 2 factorial. That moved. Took the derivative of x cubed. It's 3x squared. Cancels out the 3 in the front there and leaves me with that. Derivative of that, 5x to the 4th, I'll write this one out, over 5 factorial, cancel the factorial, and that just becomes 4 factorial. So now I've got the series for cosine. Somehow you know these, right? Like, has everybody seen these at some point in their lives? Yes is a great answer. Awesome. So let's just replace that x with ix. So e to the ix is 1 plus I. I'm just going to replace every x here with in parentheses I times x. So it's plus ix squared over 2 factorial plus ix cubed over 3 factorial. Ix to the 4th over 4 factorial. So I'm just plugging that in. And then I'm going to notice that there's a lot of powers of I in here. I'm going to kind of pull those apart from the x. So this is 1 plus ix. This is I squared x squared. And we know that I squared is -1. So that's no longer imaginary. That's just minus x squared over 2 factorial. Because I squared is -1. And then I cubed is just -I. It's just I times that on both sides. So this becomes minus I x cubed over 3 factorial. This is I to the 4th. I to the 4th is 1. And now I'm just going to have I to the 5th, which is I, and I to the 6th, which is -1. And this pattern repeats from here. See, right now we're synced up with that. And the next one's going to be plus I x to the 5th over 5 factorial minus, now it's just a -1, x to the 6th over 6 factorial minus I x to the 7th, like so. And now we're back to x to the 8th. And a nice old 1 in front, and then there's this alternation from here on out. It's not every other, so I don't want to put plus minus. Let's kind of put a plus. More stuff that follows this every 4 rhythm. Now, notice that every other term has an I in front of it, and the others don't. Group together the stuff that doesn't have an I. Let's put that in parentheses. So 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial minus x to the 6th over 6 factorial. Now I can do a plus minus. So that goes on forever. Plus, now I've got a bunch of I stuff. It's x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial, blah, blah, blah. Now we have another true plus minus, and see? Cos. Sine. Yay, now I can just use that and not worry about it. And everybody's on board, everybody believes it as much as you believe in infinity. But it's have you ever seen that before, that derivation sometime?
Not that one, no.
Not that one, yeah. It's really, really, really cool. One of my favorite math stories, absolutely. If you ever have kids, One day you'll tell your kids this to send them off to dreamland. I hope that you do that. I hope you have super nerds as kids. All right, so we got that. I can come back. Now we can do this shit. All right, Euler's identity. So I got two complex eigenvalues. Let's say I've got lambda equals alpha plus, let's just do a real example. Instead of a general derivation, let's do a nice solid example. Oh shit, I need notes. I think I have something in here. Yeah, here we go. Sehr gut. That's about all the German I know. Okay, so let's do an example. And I think this will give you understanding, and then I'll give you the general result, and you might be happy with it. You also might not, I don't know. So suppose our eigenvalues, if you want the full glorious derivation of what's going to happen today, the book has it. But I wouldn't read it from the book. I would Google complex eigenvalues, and I'll put a video up for you, because the book is not pleasant to read, I don't think. So I'll put up a full derivation of this, but I want you to see the idea behind what's happening here. Suppose our eigenvalues are, we have lambda equals I and lambda equals negative I. They always come in these pairs. They're called conjugate pairs. Complex eigenvalues always come in a pair that looks like this. There's a +1 and a -1. So, conjugate pairs. Let me write that up here. Complex evals come in conjugate pairs. Always. For anything we'll ever do, it's not true. It's the most ultimate generalization, but we're all good. And then these have corresponding eigenvalue vectors. So the vector that corresponds to this is 1i. You've actually done a little bit of this, I think. I had you actually dig some of these up on your own. And then -i is 1 minus I. And we're gonna fall back on that very first thing I put up on the board at the beginning, about the form of our solutions. So recall. And actually, there's a system that these come from, and I probably should have put that up here so that we have an actual problem. Here's the system these come from. Xy dot equals 0 minus 1, 1, 0. Xy. Make sure that's right. Put the minus down here. So that's the system we had. We went through, we found the eigenvalues, they were this. We found the corresponding eigenvectors, they were these. And we're good to go. So our solution follows the form xy of t equals c1 e2 lambda 1t times our vector 1. And I put this up at the beginning, but I just want to put it up again so that the flow here makes sense. That's t. v21, v22. Your solutions always look like this, no matter what. But now we're going to plug in I for the lambda 1, negative I for the lambda 2, and then these weird s vectors. So here we have this equal to some arbitrary constant e to the it. That's why we needed to know what that was. It's that. And then we've got 1i plus c2, another arbitrary constant, e to the minus it, 1 minus I. This is much nicer than it would have been. I'm really glad we just kind of, just like a saddle point, dove away from the general case. I don't think you'd want to come back on Monday. I did that to you. I want you to come back. So we're going to replace these guys here with the Euler's formula. So this is C1 cos t plus I sine of t times this vector, 1i, plus C2. Now, when you replace t with negative t, or x with negative x, so if I put a negative x there, it propagates inside like this. So if you replace that x with a negative x, it's cos of negative x, sine of negative x. Cos is an even function, so you still just have cos. Sine is an odd function, so the minus comes out in front. So what I'm saying here is that e to the minus ix is cos x minus I sine of x. It's the conjugate of e to the x. So this is cos t minus I sine of t times this critter. And now I'm just going to put this all together and do a little algebra. Now it's literally just algebra. I'm going to rewrite this as a big vector. And what I mean by that is I'm going to take this scalar quantity times this and have a new vector there, and then this scalar quantity times the components of that vector. Scalars hit both components. So this is going to be big ass vector C1 cos t plus I sine of t, that's times 1, plus C2 cos t minus I sine of t, times 1 again. So that's the first component. So it's not too bad. This bottom one becomes the same thing, but times I. So down at the bottom, I've got C1I cos t plus I sine of t plus C2 times negative I, because there's negative I down there, then the cos minus I sine of t. Let me erase so you got time to get with me on that. Almost done. Really, truly, almost done, I promise. My next move here is to simplify. See how this has this I here? I want to kind of distribute that and deal with the I squared it's going to produce. Here it's going to give me an I squared. Here it'll give me a negative I times negative I. I want to deal with those guys. So I'm going to rewrite this as that is equal to, the top one's pretty chill, but I am going to regroup it. So the I's, all the I stuff clusters like oil, and the real stuff pulls together like water. So the I is kind of like a suction that pulls all the I stuff together. So I'm going to rewrite this as C1 cos t plus C2 cos t. That's the real part. C1 cos t plus C2 cos t. And then I've got some I stuff, and I'm going to put it together and just pull the I out in front. And what I'll have is C1 sine plus minus C2 sine. Like that. And then that's all part of a big vector. That's I think everything's going well. And then, same game down here. Let's do a little scratch work underneath this and rewrite it just right here. So that this whole, the word critter keeps coming to mind, but I'm gonna just call it this thing. This is C1I cos t minus, so look, I got a I squared, so it's minus C1 sine of t. That I squared becomes a minus. And then here I've got C2 minus C2I cos t. And then minus I squared, minus I times minus I is just I squared, and that's -1. So this thing times that is a -1, and I get minus C2 sine of t. And I'm going to play the same game. I'm going to pull this stuff together, just the real stuff. So this guy and this guy go together, and this guy and this guy go together, because I's mix, real stuff mixes. So what we'll get is minus C1. Let's just kind of put it together. We're going to do one more move, and then we'll be done. Minus C1 sine minus C2 sine. This is looking pretty. Your mileage may vary on how you feel about that. Then I've got I times C1 cos minus C2 cos. Oh God, so good. So easy to screw this up. And just imagine if instead of I had alpha plus I beta. Same stuff, the same rhythms are happening, but just no one wants to watch that. You probably barely want to watch this, but I appreciate you staying. So do you see some lovely algebra, right? There's sines in common, coses in common. So let's just rewrite this. The top one becomes C1 plus C2 cosine of t, pretty, plus I times C1 minus C2 sine of t. So lovely. That's how I know it's going well, because it's pretty. Most of the time when math is going well, it's pretty. Not always. Remember back in the early parts of this class when you had to do all sorts of separation? Things weren't always pretty. But now we've got minus C1 plus C2 sine of t. So I pulled that minus out that's shared. And then one last one, I've got plus I C1 minus C2 cosine of t. Yes. Man, I'm glad we got through that. I'm probably as tired as you are after working through that. I'm very grateful to get through that. Because what I'm going to do now is make some substitutions. I'm going to just call this C1 plus C2, which occurs here, and then I times C1 minus C2, which occurs here and here. I'm just going to call those new things. So let D1 equal C1 plus C2. Let D2 equal I times C1 minus C2. And we have got some really elegant looking stuff now. D1 cos plus D2 sine minus D1 sine plus D2 cos. Huzzah! That's our solution. And there's not an I in sight. They're tucked neatly away into those constants, and it'll all work out. Notice, nothing imaginary, but we didn't get here without I. So the I is hidden. Let's actually make a note. I is very modest. Very modest number, because it does all the work and then just gives real the credit. I is hidden. but always lurking. Sound a little ominous.
Out of sight but not out of mind.
Ooh, I like that. Out of sight, but not out of mind. But keep it out of your mind too, when you're doing this, because it might mess you up. But it is good, yeah. All right, so now we can come back, and this is the solution to our system. So the original problem was this. xy dot equals 0. So actually, let me just write it out. It was, I had the one, y and then minus x. I don't know why I'm even putting these guys here. Let's just, sorry. X dot equals y and y dot equals minus x. That was our system. If we sketch the direction field, you'd see a beautiful current flowing. In fact, let's do that. That was the system we were working on. The null clines here are what? So x dot equals 0 when y equals 0, all along the x-axis. All along the x-axis, I have pure vertical motion. Y dot equals 0 when x equals 0. So that's all along the y-axis. Let's test some signs. S-I-G-N. It definitely need to be clear here, because there's actual signs floating about. At the point, let's just get the flow on these null clines by doing x, y, and then x dot and y dot. So at the point 1, 0, I've got x dot is 0 and y dot is -1. That means it's flowing downward. I already know this is going to be circulation, so I'm pretty much done. I could go through and check a bunch more points, and you will be able to do this eventually too, and see that you've got a flow that kind of looks like this. And the further out you get, the larger those velocity vectors go. But these are perfect circles, maybe, probably. But what we've got are trajectories that look like this. Clockwise motion. You have furrowed brow, Lou. Yeah. I maybe know why. I'll talk to you about it later. So, what is the general solution? Here's what I spared you from, but I'm going to put it in a big box, and then we'll call it a day. General. Yeah, I don't know, Lou. Good luck, general. Slow down, buddy. General solution. If, and I don't need to write the eigenvectors. This is the cool part. If lambda equals alpha plus or minus I beta. Now we just had pure imaginary things here. It gets a little more interesting when you've got a non-zero real part. But here's what your solution is going to look like. It's going to be x of t, y of t equals c1e to the alpha t cosine, hold on, I think cosine of t minus, cosine of beta t, sine beta t, plus c2 e to the alpha t sine of beta t cosine of beta t. Whew. I wonder if that's true. I think it is. Yeah, hold on. Yeah, that's true. I'm checking my notes. Yeah, good shit. All right. That's real. So when you have, if alpha equals 0, there's no decay or growth, and you just have what are called centers. We have perfect elliptic orbits. These are called centers. You'll have to figure out the direction. You'll have to test some points. But if you have a pure imaginary eigenvalue, everything just spins around the origin. If alpha is negative, I have decay. That e to a negative something t sends you careening toward the center. And here, Cormac, here's where we get those real, actual vortices headed in. So if alpha is less than 0, we have stable spirals. You still have to figure out the right direction by testing a vector or two. If alpha is greater than 0, we have unstable spirals. We'll do more work with this on Monday, but honestly, good work. You've paid the heftiest price that has to be paid in all of this today, so thank you. And that was the bargain version too. I'll put up the full version for your delight. So please, so let's try to get those portraits in by Friday. If we need to take that long, all totally cool. If you need till Monday, that's cool too. But please start checking out the web work before Monday if you could. Just check it out. Thank you, my friends. Thank you, as always.